Hello, can you hear me up the back? Sort of. I will try to talk loud, and then hopefully we can work it out. Okay, so thanks again for the introduction and for having me back. What, we all good? Yeah. How about that? Is that okay? Great. Okay. So again, thanks for having me back. So I'm going to be talking about really some relatively simple ideas in terms of control of linear systems. So this is, I guess, taking a sort of a step back in complexity from some of the things, for example, that Peter was talking about in terms of optimizing nonlinear systems. But we're really going to focus on the control part here. And so in some sense, this is sort of an abbreviated sort of first course in control theory, or elements thereof. And so really what we're trying to do here is start with some system, which might be linear, or it might be non-linear, but perhaps by looking at it in a linear way, we can still make some progress in terms of working out how to manipulate it to whatever objective we have, using feedback control. And so to jump forward, what we're going to be going through, we're going to use a relatively simple model as an example to sort of drive talking about these ideas. We're going to be looking at proportional, PID control, pole placement, and LQR. And then I might talk a little bit about a few other methods. The other thing to note is that I'll be sort of relatively frequently switching between the time and frequency domain. So if you think back to some of the material yesterday, we're kind of touching upon some of these ideas, or about the sort of equivalence between a linear state space system or a system in the time domain, which perhaps can be also characterized by its impulse response, and then the equivalent system in the frequency or Laplace domain, which can be characterized by, say, the response to forcing at given frequencies. And it turns out that each of these ways of characterizing and understanding a system have their own advantages, depending on exactly what we're looking at. So let's jump straight ahead to our model problem. So we're not being particularly creative here, looking at an example that we've considered in a few lectures so far, which is just flow past a cylinder. We're at a Reynolds number of 60, so we're unstable, but only sort of just unstable. It takes a while if we start near the unstable equilibrium to eventually have a disturbance that grows, and eventually, because this is a nonlinear system, we end up on a limit cycle. And so we're going to be using this system as motivation, in the sense that I'll take data and use that to identify a linear model. But then from there, we're just going to be looking at that linear model. So going back and actually trying to control the full system will be beyond the scope of this work, though I will talk about some other works that have used these ideas in linear controls to control actual fluid systems. So what do we do? So we can take some data, we can use sort of a modal analysis techniques such as POD to get out the dominant structures. And for this system, it's pretty simple. There's really only one dominant unstable mode. And so the POD coefficients sort of identify that. And then what we do is we look at the dynamics of those first two modes in a short time window near the unstable equilibrium. So with the thought being that the system is approximately linear here, and we identify a linear model in this regime. Oh. Oh. Didn't like one of my slides, but you might have to imagine what I actually get is a linear model that reconstructs the data both in this region which I use to identify the data, and then for a fair bit further as well. I kind of want to show it. Right, so this is actually what I wanted to show, where we have a linear system identified here, and then things sort of remain relatively linear, at least in terms of the evolution of these POD coefficients, for a fair while longer. And that's kind of good to know in practice if you were to, oh, there we go. If you wanted to try and implement a method like this, you might be able to argue that the basin of attraction or the basin where your linearity is valid is like relatively large. So I'm going to skip through the details regarding the identification of the dynamics, but essentially we can use our favorite linear modeling method. It could be something related to dynamic mode decomposition that we learnt about yesterday or a couple of days ago, or it could be something that we do again, either in the time or the frequency domain. But at the end of the day, we get a linear state space system where the dynamics are governed by this A matrix. And perhaps unsurprisingly, we find that it's unstable, which we observed from looking at what happens to the system over time. But what we see is we have two eigenvalues in the right half plane, so here I'm sort of looking at eigenvalues rather than complex frequencies. So everything in the right half plane is unstable and the left half plane is stable. So in other words, anything with a positive real component is unstable. So this is going to be our starting point for our analysis. We have a linear system that looks like this, and it's two-dimensional, so it's about as simple as one could get. Okay. So we don't want to change slides. Let's try this one more time. Okay. Hopefully I don't have to do that between every slide. So what we have, or what we can define, is not just the dynamical equation, but also if we're looking to control this system, we presumably need to have some way to manipulate it or to provide an input to it. So along with this A matrix, we can also define a B matrix, which for this case, or for this example to start with, we're going to assume only has one channel. So we input one directly into one component of the state. And then we're also going to assume that we have a single output. So that is, we have one measurement. And so what we have at the end of the day is this dynamical system that takes a scalar input and spits out a scalar output. And within that, we have an internal state whose dynamics are governed by this A matrix. And we're actually going to consider two different systems, because I think it's going to be informative in terms of understanding how we can study these systems and work out what sort of control is going to work or not work. And so we're going to look at systems always where we're outputting the second state, but I'm going to have system one where my input is in the first state variable, or the first channel, and then system two where it's in the second variable. And even though the dynamics of these two systems are the same in the sense that they have the same A matrix, in terms of designing feedback controllers, there are some sort of important differences here that we'll come to. Okay. And so just to put this in a different way, as well as talking about these linear systems in state space form, we can also look at the equivalent Laplace Domain versions. So if we know what our A, B, C, and D matrices are, although here we're going to assume D is equal to 0, so there's no direct feed-through term from the input to the output, then we can write the transfer function directly from these matrices in this way. And this operator here actually came up in Peter's last talk, where we were looking at the response of a system to a given input, where the input here goes through the B matrix and the output goes via the C matrix, but it's the same sort of idea. So anyway, we get these two transfer functions. And perhaps unsurprisingly, because we have the same underlying dynamics, they have the same denominator, which indicates that they have the same poles or eigenvalues. However, they have different numerators. So in one case, we have a 0, so that is a solution to the numerator being equal to 0, and the other one doesn't. It's worth noting here that this denominator is a quadratic, and one way of thinking about these dynamics is the transfer function ends up being a similar form to what you get with a spring mass damper system, say, except for the fact that we have this negative term which sort of corresponds to a negative damping coefficient. And that's consistent with what we have in terms of the system being unstable. So that is, any initial condition will grow in time as well as oscillate rather than decaying in time. Okay, so we have different ways to characterize this linear system. Okay, so now we want to control the system. And so the idea will be that we want to provide an input that we assume we have complete authority to choose, that will hopefully give us an output that we desire. So for example, or most simply, we might want to drive the output of our system to 0. And so how we do this is we want to somehow make our input be dependent on what our output is, or use real-time information about our output in order to determine what our input should be to achieve some desired control objective. And so really this idea is what underlies feedback control. So that is, we have this loop where the output is used to compute the input that hopefully drives the system to the output that you want. And so really what a lot of this lecture is going to be doing is studying what this K is, which is going to be how we relate our output to our input, basically. So for simplicity, we can choose R is equal to 0. So what, I should have maybe written this explicitly, but what this input ends up being is R minus whatever comes through this feedback loop. So R minus K multiplied by Y, which is this here. Or alternatively, since we know that Y is equal to Cx, remembering that D is equal to 0, our input to our system is now related to the state of our system by this Kcx term. Now, I haven't said anything about what K could be. Most simply, it could just be a constant. But more generally, it could be itself, say, a linear system with its own internal dynamics that could be designed, presumably in some way, to give desired closed-loop performance. Okay, so what should we choose K to be? So actually, to start with, and I'm going to jump to some code, like a Jupyter notebook soon, where we're actually going to implement this control. But what we're going to do to start with is to be a little bit naive, but use sort of a very common starting point, which is just to guess something. So we're going to start just assuming that we have proportional control, so K is a constant, and we're going to guess or try K is equal to 1 and see what happens. Okay. So it's not meant to be here. So now I want to... Okay. So as I mentioned before, we can upload this code to the lecture series website a little later on, but you can also access it through this link. So again, we're going to be using a Jupyter notebook in Python, and we're going to be going through and showing how some of these linear control ideas can be implemented in practice. And the key here is that we're going to be using the control toolbox in Python, which is something that you actually probably have to install separately, and so there's a link for that here as well. And I'll mention that this has a lot of the same functionality that MATLAB's control systems toolbox has, if you're more familiar with that, though there are still some aspects of things or certain functions which either aren't in the Python version or are a little bit more clunky or require a little bit more manual tuning. But more or less for what we're going to be looking at today, you can implement this code in MATLAB or Python with relatively similar syntax and functionality. Okay, so what are we doing? So to start with, I'm just defining my two state space systems. So we have our common A matrix, common C matrix, and then the two different B matrices. And then I can print them out if I want, but this is nothing different. And I can also define the transfer functions, which I can get directly from our state space systems through this ss2tf command. So there's a lot of nice shortcuts within this control toolbox that allows you to do things that you might commonly want to do when studying and manipulating linear control systems. And then I can look at their eigenvalues, and right, they should all be the same because they all have the same A matrix or the same denominator. And again, we see that they're the unstable complex pair of eigenvalues that I had before. And again, what I can also do is simulate this nonlinear system, simulate this unstable linear system. And again, both systems have the same response because I'm just running this from a given initial condition without any control input. So unsurprisingly, we get the same thing. And this is exactly what we saw on the previous plot. Okay, so now we can try to do control. So as I mentioned before, we're going to be using proportional control with a constant of proportionality of 1, just to see what happens. So again, there's a relatively easy shorthand way to implement this in Python. We can just use the feedback function to generate our closed loop systems. And then what I'm going to do, without doing anything else, is try to run these closed loop systems where I take my initial simulation and pick some point, so some time index, where I switch on my control. So let's do this. So this runs, and now we can see what happens. So I'm turning on control at about 25 seconds. And, well, in short, we see that for one of the systems, this feedback control works really well. So system 2, if our objective was to drive this response to 0, we do that. Whereas for system 1, we're modifying the dynamics, but it looks, at least by eye, that our system is still unstable. Yes? Yes, so the actuation is directly in one of the states. So, no. So I'm just using I only use that cylinder to identify a linear model, and then I'm just control on the model. It's not control on the plan. Yes, just on the model, and I'm assuming that I'm directly modifying, I guess, one of my states, which is one of my modes. So it's not physical. Yeah, we can talk more about that later. But yeah, so to emphasize, the equivalent control here would be to assume that I can be forcing in the direction of one of my modes. So it would be a sort of a non-local control. But again, we're kind of just looking at this linear system in and of itself now. Okay, so what we perhaps want to do is understand why this naive proportional control worked for one system and not for another. And if we like, although this is probably obvious, we could look at what the poles of our closed loop system are. I'm sort of jumping ahead a bit here, and we find that for system 1, so that was the one that wasn't controlled, we have an unstable pair of eigenvalues, or unstable poles, whereas for system 2, we have stable poles. So that is consistent with what we saw. But what I want to do is to go back and see if we could and this back was talking about before, we have closed loop dynamics that such that the input to our system is related to the output by this controller K. And so what that means is that our closed loop dynamics, if we go back to the state equation of our dynamical system, we can write everything in terms of X and see that we have our closed loop dynamics, which are going to be governed by this matrix, which is our original matrix, but modified by this BKC term. And so by looking at the eigenvalues of this matrix, which we should be able to know or predict for a given K, we can compute them, we should be able to say whether or not our system is stable. Or equivalently, in the Laplace domain, the closed loop dynamics for our system, where P is our plant or our original open loop system, are going to be given by this. Actually, it should be P. There shouldn't be a K there for this configuration. But that's a minor thing. The important thing is that our closed loop poles are going to be solutions to the denominator of our transfer function being equal to 0. Okay, so let's look at things in a little bit more of a general way. So in general, if we have our system being given by a transfer function of this form, and both of the systems that we're looking at are of this form, then this is sufficiently simple such that we can explicitly compute what our closed loop poles are going to be. So all that we need to do is substitute in, is basically express this equation, make this equation equal to 0, and then rearrange things a little bit, and we find that we just have a quadratic equation that tells us what our poles are going to be as a function of our controller K. So, and again, we're looking at a general system of which we have 2 examples, which are those 2 systems that we're going to be looking at. And actually from this, it becomes, if we study this in the right way, it becomes entirely obvious why proportional control with K equals 1 works for this system, but not for this system. And that is, if we look at this, for this first system, A1 is equal to 0. So what does that mean? It means that this term drops out. So we have originally this real term and then plus or minus these guys, which are either going to form a complex conjugate pair or be a positive and negative real number. So what that means is that if A1 is equal to 0 and our system is originally unstable, then there's actually no way for a constant K to stabilize our system, because we don't get anything out of this term. And then for this term, we start off being unstable. Again, I should add, if this is originally a complex conjugate pair, then either it remains a complex conjugate pair, or it remains purely imaginary if the argument of this square root is negative, or if it becomes positive, then one of these guys is positive and one of them is negative. So either way, you don't get more stable. So again, it's relatively simple to see from this equation that there's actually no way or no constant K that is going to stabilize this P1. On the other hand, with P2, we're kind of saved by the fact that we have this term here, which has a negative out the front. So what that means is that K actually makes these poles more negative, at least in terms of this contribution here. It's a little bit more complicated once we add the effect of this, but it's feasible that we should be able to control the system in this way. Okay, so again, to summarize, for a positive A1, which is what we had for this second system, a positive K will tend to move the eigenvalues towards the left half plane, so to stabilize it, which is why we stabilize system 2, but not system 1. Okay, so that is nice. It turns out that it's relatively easy to understand what we had observed empirically. But now the question, or now one question that we can ask is, well, how do we stabilize this system? So one thing we could do is, and there are obviously a lot of things that we can do, and eventually we'll introduce a lot more theory that will allow us to perhaps do this in more systematic ways. But one thing that we could do is actually choose a controller that makes system 1 kind of look more like the controlled version of system 2. So that is, if we choose a controller that basically replaces this numerator with this numerator, then I'm actually going to get a system that should have the same poles. So in other words, I get the same 1 plus pk equals 0 equation for system 1 if I choose a controller that looks like this. And again, this is not necessarily the smartest thing to do, but what we can do without knowing anything else or developing any other theory is we can use the fact that we know that our controller works for a similar system, or use the fact that we know that a k equals 1 proportional controller works for a similar system to find what can be thought of as an equivalent controller to stabilize our system 1, which proved to be a little bit trickier to control. So in practice, what I can do now is define a new controller for our system 1, where, again, I'm putting my open loop system in feedback with a k, but now my k is a transfer function. So it's not a proper transfer function because the degree of the numerator is greater than the degree of the denominator, but that's okay. And so what I can do is run this. I can look at what I get. And at the end of the day, if I look at my transfer function between my new controlled system 1 and the controlled system 2 with k equals 1, down the bottom here, I see that they have the same denominators. So the numerators are still different, but at least I've managed to put my poles sort of where I want them, or where they'll be stable. And there's sort of a technicality here in terms of basically to do this feedback, I had to go to transfer function notation because Python doesn't like non-proper systems in Statespace form, and then I had to adjust my state because it kind of changed. But that's a minor technicality, but at the end of the day, when I simulate this system, I now have a stable response for both of my systems. So that's nice. So again, I'm turning on control at a particular point. The orange curve is the original system 2, which was stabilized with k equals 1. And then the green curve is that controller that I designed to try to get a system that looked kind of like system 2 when it was controlled. They're different, though, again, because the numerator of the transfer function is different. Are there any questions so far? Okay, good. So we're going to do things a bit more systematically now. But I'll mention that really what we've started to do is look at some special cases of PID control. So that is where we have a controller with relatively simple dynamics that includes a proportional term, a derivative term, and those two are what we have here. And then we can also have an integral term. And so intuitively what's going on here is that we're taking our output and then we're saying that our control input, or the input to our system, is going to be a function both of that output and then also its integral and or derivative with time. Or in other words, if let's say our output was sinusoidal, say, then we're really sort of shifting in phase to get the derivative and the integral terms. And there are many ways and rules of thumb that one can use to tune these parameters. This type of control is still used a lot in industrial applications, for example. It's relatively simple. If you know what you're doing, it can work relatively well. Sorry, that should be a D, not a P, I realized. But it still requires potentially some sort of guessing or sort of twisting of knobs to obtain some desired behavior. And so and again, I could go back to the notebook and start playing around with these things, but in the interest of time, we'll keep pushing through. But feel free to play around with that yourselves. Okay, but more generally, if I have, say, a simple controller, I might want to be able to predict something about the performance or the stability characteristics of my closed loop system. Now, in the example that I showed, it was actually relatively simple to, from first principles, determine where my closed loop poles were. But that really relied on me only having a two-dimensional system which had a quadratic that I needed to solve for the poles, and I could use my quadratic formula, and so everything works out nicely. More generally, though, if we had a higher order system, so that is if the denominator of our transfer function was a higher order polynomial, then it quickly becomes intractable to solve. And so that motivates sort of the design of tools that can help us make these predictions without having to do the precise math. And so that motivates the root locus plot. And so what this is it's a plot of all of the poles, all of the closed loop poles that you get that are parameterized by some constant within some controller. So most simply, this could just be proportional control and looking at all non-negative constants of proportionality. Or more generally, if you can take a factor of k out of your controller, so that is, let your plant multiplied by your controller be equal to k multiplied by some other transfer function, then you can do things that way as well. And so it will turn out that it's actually possible to look at what these root locus plots look like, say in Python or MATLAB, but also it's possible to predict what they look like using a few simple rules just by hand, which is, I guess, good if you're ever stuck without a computer and need to stabilize an unstable system or something like this. But also it's good to understand why a root locus plot looks like what it does. So that's what we're going to look at now. And this, I think, will make more sense when we go through an example. So once again, it's sort of a one-liner in Python or MATLAB. We have an inbuilt rlocus command. And it will either output the plot itself automatically if you have plot equals true. I think in Python in particular, it's kind of nice to do things a little bit more manually, so at the expense of having more lines of code. But basically what I'm showing here are the root locus plots for proportional control for my two systems. So again, these are systems with the same A matrix, but different B and C matrix pairs. And so we see for system 1, remember this is the system that we weren't able to control, or that was still unstable when we used our simple k equals 1 proportional feedback. We see that the eigenvalues, or the eigenvalues are along these blue lines, which we observe never cross into the left half plane. So that's consistent. Conversely, sorry, this should be system 2, not system 1, but I can change that. We see here that as our controller gain changes, our poles, which originally were at these red crosses, move towards the left half plane. Again, consistent with what we had found empirically. Okay. So now the question is, do we understand, or can we predict why these plots look like this? And that's what I'm going to do next. So it turns out that root locus plots can be constructed or approximated using a few simple rules. So to start with, root locus always starts at the open loop poles, or the poles of G of S, which in our case for proportional control is just the open loop poles of our system. So that is why these scales are different, but we start, or one end of our root locus, which corresponds to k equals 0, is at these open loop poles. Secondly, a point on the real axis is included in the root locus if there's an odd total number of poles and zeros to the right of it. And here's where the fact that our system 2 has a 0, but our system 1 does not, starts to have an impact. Because the total number of poles and zeros for our system 2 is 3, which is odd. So what that means is that everywhere to the left of, well, to the left of all three of these guys is going to be included in the root locus. So that means there is a k value such that any point on this blue-colored portion of the real axis is an eigenvalue for our system. And actually, it goes all the way up to where this 0 is, because, well, these two poles are both at the same location. So every point to the left of this 0 has either 1 or 3 total poles and zeros to the right of it. So it doesn't particularly matter whether this 0 is to the left or the right of these poles. And then lastly, as our controller gain goes to infinity, the branches of the root locus which go to infinity asymptote to straight lines that are given whose angle with the positive real axis is going to be given by this. And it turns out that the number of these lines that go to infinity is given by the relative degree, which is the number of poles minus the number of zeros of our transfer function. So again, the relative degree of system 1 is 2, because we have 2 poles and no zeros, while the relative degree of system 2 is 1, because we have 2 poles and 1 zero. So that means that system 1 has 2 lines going to infinity, and if we use this equation, we find that those lines are at pi on 2 and 3 pi on 2, whereas here we only have 1 line, which we find is at negative pi, which is consistent with our finding regarding the real axis.